Welcome to this lecture series in linear algebra. In this lecture, we'll look at the notion of the transpose of a linear map and let us recall some relevant things. So we have seen the notion of the dual basis of a given basis. So if we fix a basis of a vector space V, then the corresponding dual basis is a basis which we write like this as notation. And the definition is this thing. You can pause the video to remind yourself if it is not immediately clear what that is. We've also looked at the notion of the annihilator of a subset of a vector space. If S is a subset of V, then annihilator of S is defined as all those linear functionals which kill everything in S, and this is one succinct way of writing that. This is the way perhaps I wrote in the lecture that I delivered, but it's the same thing. And we notice that this is always a subspace of the dual of the vector space V, and we also notice that if suppose you use a subspace of V, let me call it W, let's say W is a subspace of V, then the dimension of annihilator of W is dimension of V minus dimension of W. So we saw this also. All right. Here are some problems. As usual, one is encouraged to solve these before proceeding. And let us now discuss the notion of the transpose of a linear map. So fix two vector spaces V and W over a common base field F, which I'm suppressing from exposition. And suppose we have a linear map from V to W. Then we'll define a map in the reverse direction, which we notate like this. This is not t to the power anything. This is just a notation that we use, and this is read as T transpose. So T and then this little t is read as transpose. So we are defining what is called the transpose of the linear map T, and this is how we define it. T transpose G is declared to be equal to G composed with T. So let's look at the diagram that informs this. We have a map from V to W, and suppose we pick a linear functional on W, so it is going to be a map from W to F, which is linear, and this composite is declared to be T transpose G. Right, and therefore this T transpose G is the composite of two linear maps, and hence this is a linear map. And since this is going into the base field, this is indeed a linear functional on V, and thus T transpose G indeed lies in the dual. So it is legitimate to use this notation. So this is how we define T transpose, and just to expand this just says that if you feed a vector V to T transpose G, what you get is G of TV. So that's what the above thing reads. So this is for all vectors in the vector space V. So yeah, that's the notion of transpose. I hope I don't want to say anything else. Yeah, so one should check that this is linear. So that is an exercise. Check that T transpose is linear. Okay, a very simple exercise. And yeah, so let us look at a very simple special case of the notion of transpose. So we have a subspace of a vector space V, and we thus have the inclusion map, which takes a vector u to the same vector. And yeah, this is a linear map. This is what we have seen before. So what is the transpose of this map? So if we take the transpose of IU, and suppose f is a functional on V, then this is f composed with IU. And what I want to say is that this is nothing but f restricted to u. And this is a very general set theoretic thing. If suppose I have a function from a set x to a set y, and there is a subset A of x, non-empty of course, so then the restriction of f to A is defined as a map from A to y, which takes little a to f of A. So that's the definition of the restriction, but if you think about it, it is nothing but this composite, where the horizontal arrow is f, and the vertical arrow is the inclusion map, which takes little a to A for all A. And this is nothing but f restricted to A. So that's a very general set theoretic thing, and therefore this is nothing but that. And what we see is that IU transpose f is f restricted to U. So just a very simple instance of the notion of transpose. Okay. Kernel and image of transpose. So suppose we are given a linear map, we would like to know the rank of the transpose, let's say. Suppose I know the rank of T, can I calculate the rank of the transpose? Indeed we can. So here are two lemmas which are relevant, relevant to the questions of those sort. So let us first figure out the kernel of T transpose, and I have already written the answer. I didn't mean to, but I have already written it. So let's prove this. So this is very simple. G is in kernel of T transpose. So G is a member of W star. I shouldn't have done that. G is a member of W star, and it lies in kernel of T transpose if and only if T transpose G is 0, of course, which happens if and only if G composed with T is 0 by definition of transpose, which happens if and only if G of T of V is 0 for all the vectors in the vector space V, which is as good as saying G annihilates the image of T. So just be mindful of this equivalence. Everything else is, well, this is also trivial, but everything else is even more trivial. So saying that G kills TV for all V is as good as saying G kills all of the image of T. And yeah, so therefore these two things are equal. And what we've shown is that something lying in the kernel of T transpose is as good as saying it lies in the annihilator of the image. And therefore we have this equivalence. So one can calculate the calculate the just give me sorry about that. So one can calculate the dimension of the kernel if one knows the rank of the map T. Kernel of T transpose, I mean, you can calculate the dimension of the kernel of T transpose, in other words, the nullity of T transpose, if you know the rank of T. Okay, what about that? So what about image of T transpose? So if we know the dimension of this, we know the rank of T transpose. So therefore, this is what we would like to know, and here is how we do it. So what we will show is that image of T transpose is nothing but annihilator of the kernel of T. Okay. So first of all, we'll do a dimension argument. So dimension of image of T transpose is by rank nullity theorem dimension of W star, because the map T transpose has its domain as W star. So this is dimension of W star minus dimension of the kernel of T transpose, right? Which is equal to dimension W, because dimension of the dual is same as the dimension of the parent. So this is equal to dimension of the annihilator of the image as we just calculated. Image of T transpose. All right, but as we recalled, the dimension of the annihilator is the dimension of the parent space, which is W, because image T transpose is, sorry, this is image T. That is why this is image of T. That is what we proved. So, sorry, yeah. So annihilator of image of T is what we are concerned with. Image of T is a subspace of W, and hence annihilator of image of T, the dimension of it is the dimension of the parent. The parent of image T is W, meaning image T sitting inside W. So this minus dimension of the image of T, which is dimension of the image of T. Right? Which is well, just let me remark that this is same as the rank of T. So we've already shown that the rank of T transpose is same as the rank of T. But of course, we're trying to prove something more than that. So this is same as dimension V minus the nullity of T by the rank nullity theorem. So here all we did was use rank nullity theorem. And even here this was rank nullity theorem. Okay, but this is equal to dimension of the annihilator of kernel T. Maybe let me write it the other way. Doesn't matter. Okay. So at the very least, the dimension of these two things match, and we would be finished if we can show that one is contained in the other. So what we will show is that image T transpose is contained there. So let me maybe do it on the side. So we will show that. image T transpose is contained in annihilator of the kernel. Okay. So let G be in W star. Then we want to show that T transpose G annihilates the kernel. Right, but that's very clear, because if to do this, let V be in the kernel of T, then T transpose G of V is equal to G of TV, which is equal to G of 0, which is equal to 0. So that's it. This is all that we wanted to do, and that proves that image T is contained in that. We already showed that the dimensions matched, and hence they are equal. So in particular, this is important to know that the rank of the transpose is same as the rank of the original linear map. Okay, wonderful. And now here is something that I want to do very briefly, the matrix of the transpose. So suppose we have a linear map and we have two bases, B and C, of V and W respectively. The elements of B are written V1 up to Vn, and the elements of C are written W1 up to Wm. And let's say we have the dual bases. So these, B star denotes the dual basis of B and C star denotes the dual basis of C. Then the claim is, if we know the matrix of the map T with respect to the original bases, then we also know the matrix of the transpose with respect to the dual bases, of course in the correct order, and that just turns out to be this AJI. This is going to be an N cross M matrix. So what I'm trying to say is that if suppose this was the matrix of A, B, C, D, E, F, if this were equal to the matrix of T with respect to B and C, then A, B, C, D, E, F would be the matrix of T transpose with respect to the dual bases C star and B star, and just unravel the definitions of everything. What is the meaning of the matrix of a linear map? What is the meaning of the dual bases? What is the meaning of the transpose? And it's just a very simple exercise, and I highly recommend you do it, because then all these notions will sink in. Okay, so now we want to do something very interesting, which I would call functoriality. It is functoriality, but we don't need to go into the details of what is the general notion of functoriality. So what we have is, we have, suppose, vector spaces u, v, and w, and we have a linear map A from u to v and a linear map B from v to w. Then we get a composed linear map, which we write like this, B composed A. So that's nothing out of the ordinary. So what one can do is, using B, one can create a map from W star to V star just by taking the transpose of B. And similarly, one can go from V star to U star by taking the transpose of A. Question is, what is this map? Well, of course, this map is nothing but, by definition, the composite of A transpose with B transpose. That's what that is. But can we say something more about this, rather than just this abstract description that you just compose them? Can we directly say what this is in terms of A and B? And of course, a natural guess would be that it is the transpose of B composed with A. So are these two things equal? Yes, indeed they are. And here is our theorem. It's that B composed with A transpose is same as A transpose composed with B transpose. Right? And all we need to do is check what? So to do this, I want to show the following. I want to show that for all G in W star, the following holds, which is B composed with A transpose G equals to A transpose of B transpose of G. That's what it means to say that these two things are equal. And we can do this immediately via means of a diagram. So let's say, yeah, so we have V, we have W. So take G, and what is this guy then? I wished this was vertical. Anyway, so this guy is what? This guy is B transpose G. That was the definition of transpose. Now, if you compose that with A, what you would get is this composite would be A transpose of B transpose of G. Just look at this triangle. We have a linear map from V to F. You compose it by A. By definition, that would be the A transpose of that guy. So that's nothing very complicated, right? But at the same time, what we have is we have this arrow. This arrow is what? This arrow is B of A, meaning B composed with A. And now just look at this triangle. So here what we have is we have this guy G, which is a linear map from V to F, and you compose it by some linear map whose name is B composed with A. What you are going to get is this guy is same as B composed with A transpose G. And therefore, this is equal to that, and that is precisely what we wanted to show. So it's just a diagrammatic
Sorry,
proof.
I can't make a phone call with your iPad.
I don't know what happened there. Siri came into existence, certainly. I'm sorry about that. So all we are trying to say is that this guy is equal to that guy, and that is what we wanted to show, and therefore this holds. So the upshot is, once we have a diagram of linear maps, where the cities are vector spaces and traffic is linear maps, you can kind of just flip that diagram by taking its transpose. So the vector spaces become duals, and the linear maps becomes transpose. So the notion of transpose is just you could just call it dual of the map T. That would be a better name. So instead of calling it transpose, I should have called it dual of the map. But in literature, transpose is used. That terminology is used. So just every triangle or every commutative diagram gives rise to another commutative diagram, where you decorate these vector spaces by star symbol and reverse all the arrows and decorate the linear maps with the transpose symbol. That's all. Okay, that's great. Lastly, there is this notion of naturality. Again, we don't need to know what this means in general. Only in this context we are interested in. So fix a linear map T. Then that gives rise to a linear map from W star to V star, which we call the transpose. And then one can take its transpose, because after all, this is also a linear map. So you can take its transpose to get this guy. Okay. Now, forget about that guy for the moment. What we have is we have a linear map T from V to W. And we have these natural identifications. So what these do is, I'm sure you remember, this takes V to what we notate as that. And this is a map from, of course, V star to F, which takes F to FV. So that's the definition of that guy, and hence it is a member of the double dual of V. Similarly, we have the same guy here, the cousin of it. That is that. Right, and these are isomorphisms, as we already know. These are linear isomorphisms. So if you start with a member of V double dual, go up via this isomorphism, because isomorphisms can be inverted. So you go up, you go via T, and then you come down. You get something here. So that is some linear map. This is some linear map, whose description is, first you invert this guy, then you compose with T, and then you compose with phi W. What we want to say is that our claim is that this is equal to T transpose transpose. So this is what we want to show. So the theorem is phi W composed with T composed with phi V inverse equals to T transpose transpose. But first, let us look at what is the message of this theorem. So what it is trying to say is that, first we notice, if we forget all about linear maps, all these T transpose for the moment, we notice that there is only an artificial difference between a vector space and its double dual, because of this, it's just a change of names in some sense. The vector V now looks a little hefty, that's all. So there is an artificial difference between V and V double dual. What we are saying is that there is only an artificial difference between this map, which you get very naturally via these identifications, and the linear map T. So T transpose transpose is Just like v dual dual is same as v under this artificial difference. Similarly, t dual dual is same as t under these artificial differences, and that's what we're trying to say. So that's the message of the theorem, that essentially the double dual of a vector space is same as itself naturally. In the same way, even that identification is preserved even when you move into the world of linear maps. So I'm just saying that it's a more deeper isomorphism between two vector spaces than just these two vector spaces being isomorphic via some map. So that's, if that makes sense. If that doesn't make sense, ignore it for the moment and let us just prove it. So here is what we want to do, and one can do this via diagrams, but perhaps it's best to do this directly. So let G in yeah, what we want to show is that for all V in the space capital V, we have T transpose of this person is equal to that. So this is what we want to do. So okay, so what is the right hand side? What is the right hand side? The right hand side is just this. Why is that? Because if you feed this to that map, you get V, right? Because little v maps to that guy under phi super v, and if you invert, you get this guy maps to v under phi super v. So this is what we want to show, right? And to show this, what do we do? Yeah, so this is same as asking for this being true, right? Because t of v is a vector in W, and therefore this is equal to that. So we want to show these two things are equal. And now this is a member of W double dual, and this is a member of W double dual. So how do you show two members of W double dual are equal? So now our aim is to show that fix V. Yeah, so here is so fix V. Want to show that by the above working, that this is the case. T transpose phi super V sub V equals phi W TV. And to do this, let G in, should I call it G? Wait a second. Yeah, G is fine. So G in W star. So we want to show that we are just reducing our wants to something simple. That's all. Want to show that T transpose phi VV of G equals to this. Right. So what is this? What is that guy? That is equal to G of TV. That's the definition of this map. So that is G of TV. And what about that guy? That is equal to, yeah. So but T transpose phi V capital V operated on G is equal to, by definition of transpose, this is equal to even I'm getting confused. So this is nothing but phi V super V T transpose G. So just think about that. We let me make a comment. So if I have a map from, let's say, a vector space X to a vector space Y and call that map A, then A transpose of something in the dual of Y operated on a vector, let me not call it G, something, let's say phi, operated on a vector in X, this is equal to phi of AX. Right? That's how transpose behaves. And that is exactly what we did. So think of T transpose as a single guy. So what we have is the dual of, or the transpose of this guy acting on a vector or a functional on W star, and then you're feeding this vector in W star. So it will be equal to this. So just convince yourself that this is the case. And now we use the definition of this guy. This is equal to, I don't have space. This is equal to T transpose G, and you feed it the vector V. But that is equal to G of TV. Again, using the definition of transpose. Okay. So maybe I should have taken it to someplace else. Cut, paste. It's very... Anyway, I'm sure you follow. So all this calculation shows that this is equal to that, and this anyway is equal to that, and therefore we have indeed shown that these two are equal for all members G of D of the dual of W, and hence these two are equal for all vectors V in capital V, and hence indeed this holds. So it looks a bit complicated, but it is not. Okay. This is all that I wanted to say. So as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.